Welcome to the deep dive. Today we're diving into, well, one of the biggest puzzles out there, Mars. You look at it and you see these incredible features, huge canyons, old riverbeds, clearly shaped by water, right?
Absolutely. Evidence of liquid water flowing sometime in its past.
Yet today, it's just this freezing, dry desert, completely barren. So the question, the one that's really bugged scientists forever, is what happened? Why is Mars like that when Earth is, teeming with life?
It's a fascinating question. And that's what this deep dive is all about. We've got some amazing new data, particularly from NASA's Curiosity rover. And there's also this really important new study just published in Nature led by Edwin Kite. Our goal today is to unpack this new idea, this sort of compelling explanation for why Mars seems almost, well, predestined to be a desert. And why it took such a different path from Earth.
And for you listening, this isn't just about Mars, is it? It's bigger than that.
Oh, definitely.
Understanding Mars helps us figure out what it actually takes for any planet to support life. It really frames that whole search for habitable worlds elsewhere. But let's start with that past water. The evidence, you said, is strong.
It's incredibly strong. You can literally see these giant river valleys carved into the surface. Old lake beds, too. It paints this picture of a very different ancient Mars. A Mars with a climate that could support liquid water.
Which just makes its current state even more mysterious, right? Like a ghost of a different planet.
Exactly. It's a history written in stone, or, well, Martian rock.
And we're at a pretty amazing time to be studying this. People talk about a golden age for Mars exploration.
We really are. I mean, think about it. 2 nuclear-powered rovers driving around on the surface, Curiosity and Perseverance. Plus, this whole fleet of orbiters from different countries circling the planet.
So it's not just more data, it's like a whole new level of investigation. We can probe the path in ways we couldn't before.
Precisely. It allows scientists to really dig deep, looking for clues, for the fingerprints of whatever environmental shift happened there. And, to understand what went wrong on Mars, it helps to look at what went right here on Earth, why Earth stays so balmy and mild, the scientists sometimes say.
Okay, yeah, Earth's stability mechanism. It's all about the carbon cycle, isn't it?
It really is. Think of it like Earth has this incredibly effective thermostat. You've got carbon dioxide, CO2, in the atmosphere. That acts like a blanket, warming the planet.
Right, the greenhouse effect.
Exactly. Now, as things warm up, certain chemical reactions speed up. These reactions pull that CO2 out of the air and lock it away in rocks. Geologists call it carbonate formation.
Okay, so warming leads to CO2 removal, which cools things down.
Sort of, but there's another part. Over very long timescales, millions of years, volcanoes erupt. And that volcanic activity, we call it outgassing, releases CO2 back into the atmosphere.
Ah, so it's a loop. Removal into rocks,
Yeah.
release from volcanoes.
Precisely. A feedback loop. It draws down CO2 if it gets too warm and replenishes it if it gets too cool, keeping Earth, relatively speaking, stable and habitable for ages. It's this beautiful balance.
Okay, so that's Earth's thermostat. Now, back to Mars. Does it have anything like that? Or is its system just broken? This is where that new hypothesis comes in.
That's exactly what Edwin Kite's model addresses. It suggests Mars does have warming periods, but its system is fundamentally different. It can't sustain them. It always seems to snap back to being cold and dry. The carbon cycle, well, it works differently, making warmth the exception, not the rule.
So it self-regulates as a desert planet, as the study puts it. What kicks off those brief warm spells then?
Well, the trigger seems to be the sun itself. Our sun gets gradually brighter over billions of years, about 8% brighter every billion years, give or take. As the sun warms up, the models show that, yes, liquid water can start to flow on Mars for a while.
Okay, sun brightens, water flows. Mars starts pulling CO2 into rocks like Earth does.
Yes, initially it looks similar. Water appears, carbonate formation starts happening, CO2 gets locked into rocks.
There's a catch. A Martian loophole.
This is the really crucial difference. Mars, unlike Earth, is pretty much volcanically dead, or at least extremely quiet. The average rate of volcanic outgassing, that process of releasing CO2 back into the air, is incredibly slow on Mars, maybe non-existent for long periods.
Ah, so it can pull CO2 out of the atmosphere when water appears.
Exactly.
But it can't put it back in.
Precisely. There's no balance. Earth has the volcanoes constantly replenishing the atmospheric CO2, acting as that counterbalance. Mars doesn't, or at least not nearly enough. So as soon as liquid water appears and starts forming carbonates, it just strips the CO2 from the thin atmosphere really quickly.
Peeling its own warming blanket off itself.
You got it. And that inevitably swings the climate right back to being cold and dry again. The water freezes or evaporates.
And the result, according to these models, these warm periods are short.
Very short, geologically speaking. And they're followed by these incredibly long stretches of desert conditions. We're talking potentially 100 million years of cold, dry desert between habitable periods.
100 million years. Wow. I mean, think about life trying to get a foothold. 100 million-year ice age. That's just brutal.
It makes sustained evolution incredibly difficult, maybe impossible for complex life. It's like the planet keeps hitting reset. And, for a long time, there was this big nagging question. Okay, if Mars did have a thicker atmosphere in the past, needed for that liquid water, where did all the carbon go?
Right, the missing atmosphere problem. Scientists were looking for its tomb, weren't they?
They were, for years. The most obvious answer was carbonate CO2 locked in rocks, like on Earth.
But the early rovers, like Spirit and Opportunity, they didn't find much carbonate rock, did they? That was part of the puzzle.
Exactly. They found sulfates, clays, but large amounts of carbonates were conspicuously absent in the areas they explored. It didn't seem to add up.
So the theory was there, but the evidence was missing. Until Curiosity.
Until Curiosity. This is where it clicks together. The model Kite and his team developed relies heavily on a discovery Curiosity made, announced just earlier this year. As Curiosity has been climbing Mount Sharp, this huge mountain inside Gale Crater, it actually found significant amounts of carbonate-rich rocks.
Ah, finally. The smoking gun. Or at least strong evidence for it.
Strong evidence, yes. Now, they still need to figure out exactly how widespread these carbonates are across Mars. It's not definitively solved everywhere yet.
Sure, more work needed.
But finding them there, in those ancient lakebed sediments on Mount Sharp, provides that crucial physical evidence. It's a potential tune for that missing CO2, supporting the idea that carbonate formation did draw down Mars's ancient atmosphere when water was present.
It connects the climate model to the actual geology found on the ground. That's huge.
It really is. And it underlines the importance of these rover missions. As one of the study co-authors, Benjamin Totolo, and I'm paraphrasing slightly, the chemistry measurements these rovers provide are just essential.
Essential for understanding how planets become habitable and stay that way.
Exactly. And for guiding our search for other potentially habitable worlds out there in the cosmos. It's all connected.
So if we pull all this together, the big takeaway from this deep dive seems to be Mars isn't just a desert now. It's almost meant to be a desert. Its natural state leans that way.
That's the core insight, yeah. Its own geological and atmospheric system seems to actively push it back towards being cold and dry. Those periods where water could flow, where life might have had a chance, were probably fleeting exceptions, interruptions in a long history of desert.
A self-regulating system, but regulating towards dryness, not life.
Pretty much sums it up.
Which really makes you think, doesn't it, for you listening? If Mars, our neighbor, so similar to Earth in the early days, if it struggles so much to hold on to habitability, falling into these vast dry spells, what does that imply about how rare truly long-term habitable planets like Earth might be? Are we just incredibly unique? Or maybe just incredibly lucky?
It's a profound question, and maybe it's not just the carbon cycle. What other factors, what other delicate balances might be needed to keep a planet friendly to life for billions of years like Earth has been?
Definitely something to chew on. Thanks for unpacking that fascinating research with us.
My pleasure. It's a compelling story Mars is telling us.
Indeed it is. That's all for this deep dive.